Hello, yeah, everyone. A very good afternoon. So nice to see you all online. Okay, so this is a first tutorial. So let's just quickly see what we have learned in the last 2 weeks' time. Okay, so for the summary of the first introduction, first section. So the ceramic we said ABE. So you must have somewhere you have a non-metal. So we say either A metal or non-metal, B is non-metal. Okay, so no matter what, you need to have at least one non-metal. Then you can form a ceramic. So we said this is actually, I hope you have this big picture already because we are preparing you for your final year project, okay? Because you have to be very clear what you're presenting to your supervisor and your examiner. So are you telling them it's a subatomic structure? So whether it's ionic or covalent, or you're talking about atomic structures, which is either crystalline or amorphous, or you're talking about like nanostructures and 0,1D3 special structures, okay? And most likely you will be more or less like these two level, okay? So micron level, which is grain size, shape distribution, grain boundary, all this blah, 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 okay? So please look for the details in the notes, and all this is quite related with your FYP. And also, as I said, we're preparing you for your FYP. So this is more or less like a big picture of what you're going to give the data to your supervisor. Okay, so as we said, structure is a huge thing in ceramics, right? We said the material science is art of finding the relationship between the process, structure, and the properties. So the structure is the one of the three big things in our material science. Okay, so you should know very clearly what you are presenting to the other people. Okay, so you can talk about it in different levels. So this is structures. Then we also talk about what is traditional and advanced. We said, oh, the advanced one, which means we can control the structure in a much better way. So orders for magnitude finer and uniform. Okay. And also we talk about few terms like structure, material, function, materials. What are they? So the structure, whatever structure means that they're supposed to bear the mechanical strengths. Okay, and the functional is all the rest. Okay, so then the summary we talk about if you want to determine the crystal structure. Crystal structure is which level? Crystal structure is this level 2, okay, level 2, atomic level. Okay, the crystal structures, you need to know it's a charge balance. You have to make sure charge balance. This is very universal rule, and RC over RA. So this RC over RA, so which means if we know the radius ratio between chi and ion, so we can determine the Cornish number already. Okay, but please bear in mind this RC over RA is more applies to the compound which have more ionic okay? So as we keep saying, so this is the third criteria, which is a little bit special here. So which is what we call is the percentage of ionic. Let me change the color, okay? The percentage of the ionic bond. So let's see if you have some materials which have more covalent bond, so you cannot use this RC over RA anymore. Okay, so this one more or less applies to more ionic bound compounds. Okay, and also we learned rock salt. A rock salt is more or less like this. It's very famous, this structure. Okay, ionic is very ionic, and Cornish number is 6, and also you have 2 FCC. 2 FCC interlock with each other. Then we have CCNO chloride, again very ionic. So you have the Cornish number, which is 8. You use BCC to remember, but of course it's not the BCC, right? Okay, and this is a special one. This is a special one. So zinc blend. So this zinc blend, it is actually relating with this one. Okay, 2 and 3. So you can use this RC over RA to determine. But zinc blend, so zinc blend also, although the RC over RA tells you the Cornish number is supposed to be 6, but the problem is they have more covalent bond in between, because in the periodic table they're more close to each other, right? So in this case, so you the same number become to 4, for example, like 1, 2, 3, 4. Okay, 1, 2, 3, 4. You have 4 Cornish numbers. Okay, so this is binary case. Then we also talk about perovskite. So perovskite, so this we just need to know that in corners, if this one stays at the corner, so these atoms cannot be owned by this cube already. Okay, so you because this at the corner position, so they actually share with 8 cube together. So that means in one cube it's supposed to be only 1 out of 8. Okay, so if it has edge here, so let's say if the atom is at this edge, so then you can imagine the edge, right? So they have one on the left and right, and also on the behind and the front. Okay, so this. Okay, so these are the edge, and the face is easier. Face is just this face, which is this one. So only share with one extra navel. So which means you have to share with 1/2. So body is 1. Okay, so this concept is used very, very often in material science. So remember later when we do the calculation. So if the cube, they don't stand together. So we said we have 6 faces, right? But once they come stand together, which means you have neighbors now. So this surface does not belong to you alone anymore. Okay, you have to share with other people, with other cube. Okay, so this is a very important concept in material science. Okay, so quickly, I think this is a very straightforward, simple this geometry. So minimal chi-i radius ratio for this number, this is 8, so it's a BCC. As I said, use BCC to remember. Okay, so and also quickly review. So we said if you want a stable structures, okay, so make sure so that in contacting, which means you're either in contacting somewhere like this or this. Okay, you have to in contact. Okay, and also what we can calculate is only this case, because this one give you the minimal, this is what we say is either critical or minimal RC over RA. Okay, because this one, right, the anion is the smallest case, right? This can be bigger. Okay. Okay, so RC over RA is going to be the minimum case. So in this case, most of the time, not only the ion need to be in contact with the chi-ion, but the ion is also need to be in contact, because this is most close packed case. Okay, so RC over RA. Okay, then you have charge balance, and also when we talk about this one, we're more talking about ionic bonding. So continue. Okay, so how can we do, right? It's actually a very simple geometry, right? So for example, we use this Q and P. So Q is the Q M P. Okay. Okay, so you can see we use this Q and P. Use this one. Okay, so obviously QP. So QP. So QP is here, right? QP, so because as we said, the ions need to be in contact. So now you have half RA, so in the end, you're going to have 2 RA, right? Okay, then MQ, you have the cross, MQ, which is this one, MQ. So obviously you can see they're also crossing a half of a RA, sorry, a 1 RA and the whole, these are 2 RC, right? Because it's a radius 2 RC and also another RA here. So that is why this MQ, so this MQ, which is Y here, so MQ, which is Y here, okay, so it's going to equals to 2 RC plus RA, okay, so RC plus 2 RA, okay. This is just for you to view, but this one is easy for you to understand, okay. Then only the tricky thing is MP. So MP, okay, so MP, which is this one. So MP is actually also pretty straightforward, right? Because this is another right angle here, and obviously this one is 45 degrees. So 45 degrees, and also you already know this 9 is supposed to be 2 RA because they have to be in contact. Okay, so that's why we have a 2 RA here. Then you have a 45 degree here. So then this X is very easy to get. Okay, so that's what we put here. So X squared equals to 2 RA squared plus 2 RA squared equals to 8 RA squared. Okay, it's a very straightforward simple geometry thing. Okay, so now we have X plus 2 RA. We use this MQP equals to Y. So Y we just said it is 2 RA plus 2 RC. So then we just extend. So this X is equals to 2 RA square root 2 square, because we said this is 45 degree. Okay, 45 degree. Okay, then plus this one, plus this one. Okay, then you can just expand this one. You will get 12, right? Because this is 8, then yes, plus 4 equals to 12. 12 RA square, and then you have 2 RA plus 2 RC. Okay, then what you can do just this both on both sides, you put a square root, then you will get 2 square root 3 RA equals to 2 RA plus 2 RC. Okay, then the rest is just a very easy manipulation. Then we get RC over RA is going to equals to this value. Okay, square root 3 minus 1. Okay, so RC over RA equals to square root 3 minus 1. Okay, so this is the proof. Okay, so it is pretty straightforward. So as I said, so it's just a simple geometry thing here. Why we can calculate, because now it's a minimum case. Minimum case, and most of the time the ions also need to be in contact. So it's easier for you to calculate. Okay. So let's continue. Okay, question 2 and question 3, although I never explained in the class, but actually it's very important because this is the first step. You go to lab for your FYP. Okay, so for example, the question 2 is the easiest one, right? Just ask you to get 1 mole of barium titanate. So this is the raw powders, starting powders. This one is the end product. Okay, so use a simple thing here, 1 mole. Calculate what is the grams, how many grams of the starting powders to produce 1 mole of this. Okay, so it's a pretty, it's again what you have already learned, but it is so important and critical steps in the lab. Okay, so we again just this is a very basic rule for process of ceramics. Okay, so you have a flour, right? We said flour, the ceramic powder with sintering additives. Then you mix. Okay, bake a cake, sieving to break down the agglomerations and form the shape, which is grain parts. Okay, and this is essence of sintering and the firing. Okay, so that is the essence. Okay, but the step one. So that is the first step you need to do in the lab. You have to get powder A pass B. In the end, you will get AB here. Okay, so of course, right, you need just get the weight and how many powders you need put in. So this is very first step in the lab. You need to use a balance to have the weight. Okay, so let's continue. Okay, so the steps, I think I just write it in more details, but it's very straightforward. So the step 1, you have to write the equation first. Okay, so make sure the equation, the right and left is balanced. Okay, then identify the molar ratio of the left and right, and calculating the molar weight of the left and right. Okay, then identify the weight ratio. So this is the most important step. So in the end, it is the weight ratio determines. Okay, you need to get the weight ratio for reactants and products, and calculating the amount of reactants according to the amount of products. Okay, so check. Look, the units have to be the same. Okay, so again, as I said, you learn in your high school, but still let's quickly review. And because our experience is based on past years, students, it actually is quite easy to make mistakes. You know, even the first step you get it wrong, so you can never get any end products. Okay, so just be very careful here. So for example, the first one, we write the equations. Let's see. The starting one, barium carbonate and titanium. Okay, so barium is 1. Barium is 1, titanium 1, titanium 1. Okay, carbon 1, oxygen 5, and 5. Okay, check. Okay, which means what is the molar ratio here? What's the molar ratio here? Jay? Watching? What's your answer? What's the molar ratio? Actually, it's very simple. Okay, 1, right? You need 1 mole, 1. Okay, so identify the molar ratio of reactant and product. So obviously you need 1 mole of barium carbonate react with 1 mole of titanium to form 1 mole of barium carbonate, right? Okay. Yeah, thank you, Jay. Thank you. Okay, so let's continue. So this is step 2. I'll get a molar ratio. The third step, you just simply calculate the molar weight. Okay, so this you can get in the table, periodic table. So barium, which is 137, carbon, you know, is 12, oxygen is 16, but you have 3 here, you need times 3. Okay, so this one you can just calculate by yourself. titanium is this one, so barium this one. Okay, so all these are, if I'm going to examine you, I will give you all these values, don't worry. Okay, so so obvious, because this question is simple, right? This question is because I asked you, give me 1 mole. I'm the boss, give me 1 mole of barium titanate product. Okay, so which means the boss will get, because it's 1 mole, right? So in the end we'll get 233.21 gram. Okay, so you need put in 197.34 gram of barium carbonate and 79.88 for this titanium. Okay, so what we put here, so since 1 mole and 1 mole. So this one is an easy one because it's just 1 everywhere. Okay, so question 3 is the one which is more common. So most likely your supervisor will say, hey, this barium titanate, the property is not nice. So I want to dope something in, which means maybe I want to change half of the barium with some other elements. So this is very more often, this more often happened in research. Okay, so let's see the question 3. So as I said, right, for example, your barium, the property is not nice. Maybe I just change half of the barium with strontium. Okay, so again, the starting powders because now you have strontium, right? You need to get raw materials. The raw materials is strontium carbonate. Okay, barium titanate and titanium. Okay, again, okay. And also, I already tell you that molar ratio is 0.5, 0.51. Okay, I just complete reaction. Of course, we have to assume complete reaction can take place. Okay, so this is the very first step. As I said, you have to assume that you're going to have a complete reaction. Okay, so and also your industry supervisor or industry boss will never say, give me 1 mole. Right? It's very weird, right? This person. Okay, so most likely he will ask you, give me 10 gram, 100 gram, or 1,000 gram. Okay, this is more often. So if we want to make 1,000 gram of strontium barium titanate, so how many raw materials we should ball milled and sintered? Okay, so again, follow the steps. Simple writing equations, molar ratio, and molar weight. So this is an easy one. So first of all, so we said, okay, left and right. Let's check whether they're balanced or not. Okay, strontium half, barium half, titanium 1, carbon half, 3, half, and then you have 1. Okay, and oxygen half 3, and 2 equals to 5. Checked. Okay, so you can check that although if you see I already put here, even though the actual formation of strontium barium carbonate involves many different intermediate phases, there's a lot of intermediate phases, but we can always write this first equation first. Okay, if you don't even start from here, you will get nothing. Okay, so obviously, let's assume this is the equations and we can get the final things. Okay, so obviously this one, the molar ratio now, it is 0.5, 1, 1, 1. Okay, 0.5, 0.5, 1, 1. Okay, so continue. Okay, so again, of course, calculate the molecular weight. Okay, so as I said, when we come here, the most important step is actually not the molecular weight. It is actually is a step 4. We said step 4, which is a real weight ratio. This is step 4. Is the real one. Okay, so identify the weight ratio of the reactants and products. Then we can calculate amount according to the amount products. Okay, so so how can we get weight ratio? You simply just use molar ratio times molecular weight. This is coming from step 2. This is coming from step 3. In the end, this is your step 4. You just times them together. Okay, times them together. You will get, this is weight ratio, which means what? Which means if you want 208.355 end products, okay, so you need to put exactly 73.815 strontium carbonate, 98.67 barium carbonate, and 79.88 titanium. Okay, so that is the weight ratio. Okay, so that's what I put here already, right? So this is weight ratio. So 17 here, 19 here, react with this one, you will get, actually in the end, this is the 208.355. Okay, strontium barium titanate. Okay, so now of course, right, because what I need is not some like 200 something, I need 1000. I need 1000. Okay, so what is the X and what is the Y? What is this here? This is also very simple, right? So you just need to make sure that ratio is the same. The ratio is the same. You just put the ratio here, the ratio here, the ratio here, it equals to this ratio. Okay, everything have to be proportional. Okay, very straightforward. Okay, so as I said, this is a super simple things for many of you, but as I said, this is the first step if you go to the lab to do any ceramic bulk materials research. Okay, so this is the very first step. So make sure you won't make mistakes here. If you make mistakes here, it's very difficult for you to further on. Okay, so then we for strontium, I3 1000, so something like this. Barium carbonate is something like this, and for this titanate is this. Okay, so this is question 3. Question 3. Okay, so now we move to the question 4. Calculate the energy change for oxide as our average particle. So now we have small one, then become bigger one. Assume the molar volume of the oxide, which is this one, the surface energy, which is this one. Okay, so how can we do? Okay, so let's quickly review what we have learned in the class, which is the page 21 case. Okay, so let's see. Quickly. Okay, so in the class we said, so for example, you start with one sphere. So obviously now what is the gamma here? Tell me, gamma what? Can type quickly. Gamma J, Qishang. Yeah, Odeda. Okay, excellent. RSV. Okay, so you start with particles. They are in contacting with the solid is actually contacting with vapor. Vapor here, vapor outside. So you have gamma SV. So as we said before, so energy equals to what? Total energy equals to gamma times what? Gamma times what equals to the energy? Can type someone? J? Yeah, excellent. Thank you. Thank you. Okay, area. Okay. So gamma times what equals to force? Gamma times what equals to force? Thanks. Gamma times what equals to force? Excellent. Good, very good. Gamma actually times length equals to force. Okay. Sorry, the mouse cannot write properly, but can you just guess, right? Just follow me. Gamma times length equals to force. Okay, so obviously now, so if I have a surface area of this one particles, okay, so then you know for one particle what is the total surface energy, right? Then, for example, I know there's an n number of the particles. Then I know I just times n. Then I get the starting one. Okay, then after centering. So for each of the spheres become one cube. Okay, and now the cube is not standalone anymore. The cube is actually just in contact with each other. So you change the surface now. Okay, so let's continue. First of all, let's starting the original surface area before centering. So we said we use area for one particle, so times n times gamma. So n, how can we calculate? Because we assume everything is molar. This is molar weight, so molar weight, okay? Molar volume, okay? So in this case, we said, okay, in this volume, then we just divided by each of these particles, okay? Volume of each. So each of the 4/3 pi, this is R cube. So then we will know in 1 mole, you are going to have 1.5 times 10 power 14 number of particles, okay? So then area, this is area for one particles, which will be 4 pi r squared. So this is for one particles. So you times one particle area times n number of the particles, then you get this one gamma actually is SV, because the surface actually the solid is in contact with the vapor. So which means now you start with 118J. Okay, so then again, we move quickly again to another one. So for example, so we said, okay, you have a cube here, which is solid and solid. Okay, so first of all, right, if you have a cube, if you stand alone, so please tell me what is the gamma here? Stand alone. So which means you're still in contacting with vapor, right? So in this case, it's still SV. Okay, but now because it's centered them together, so you change your surface from gamma SV to actually gamma either SS, right? Because it's solid and solid, or gamma GB, right? Correct. Very good, very good. Okay. And also we have another name we call it gamma GB, but actually it's gamma SS. Okay. So gamma SS and gamma GB, it's equals to use this equilibrium. We have provided in the notes. So very simply, you will get gamma GB is slightly higher than the gamma SV. So it's 1.28 J. Okay. So again, now you need to calculate. It's still the same thing. You need to calculate the area. So we said, okay, so I think the only tricky thing here is how can you determine the surface area? Surface area, okay? Because this one still have students ask questions, okay? Send me emails, okay? So basically you can see, so if this one, the cube standard norm, so obviously you're going to have 6 faces, right? If it's standard norm, 6 faces, okay? But once it's centered, so for example, for this one, right? You on your right hand side, you're going to have another cube. Am I correct? On your left hand side, you also have another one. On the top, you have the back and the front, top and bottom all have, which means now all your surfaces does not belong to you anymore. All the surface does not belong to you anymore. Okay, so this surface, all the surface, you have to share with one label. Okay, so that is why. So for this case, if you are in contacting with air, so actually you have 6 surface. Okay, 6 surface A. If this one is A, is A, the length is A, so which will be 6A squared. Okay, but now you stand together, so your surface is going to share with one more label. So each of them is supposed to be only considered as half. Okay, so as we see in the perovskite case, the same thing, like the oxygen atoms, if you stand at the surface, you actually share with another label. Okay, so you can only consider as half of atoms instead of 1 full atoms. Am I correct? Same thing. Okay, so first of all, so we know that we have to calculate the length, right? Length of A, length of the cube. Okay, so again, they have supposed to have the same volume. Okay, so A cube equals to 4/3 pi r. Okay, so this one is the volume of the sphere. This is volume of the cube. So quickly you can put the r in. R is 0.5, right? Or 0.25. This is 0.25. Okay, so then you will get in the end, you will get this 0.4 microns. Okay, so that is A. Okay, so then we also already know, right? For one cube, so the surface area we change from 6A squared to what? Can you type? For one cube, so originally, if you standard norm, you're supposed to have 6A squared, right? Because this is A squared, you have 6 of them, so it will be 6A squared. But once you need to be in contact with each other, once you form green boundaries, okay? So this have to be halved. So we said have to be 3. From 6 change to 3, okay? Yeah, hopefully this is clear because a student emailed me about this one. Okay, 3A squared. Okay, again, numbers, right? You know, you still have a number because it's 1-to-1 change. You change from 1 sphere to 1 cube. So in the end, you have how many spheres? You have how many cube? Okay, so the surface of the green boundary is going to be 72. Okay, 72. So now you tell me, I need a times what? Times gamma. In this case, gamma GB. Okay, so in the end, it will be 1.28, which is gamma GB times 72 is 92J. So we said we start from 118, we end up with 92. So this one obviously is going to happen because no matter what, if your total energy is going to reduce, it's going to happen. You're starting from 118J, you end up with 92J. So the difference between here, we call it a driving force for centrings. Okay, so this I will very quickly, just a few minutes to explain what we have already explained in the class. Okay, so now we see the second scenarios. Okay, the first scenario is you have one sphere become one cube. Okay, then cube stacked together. But there's another possibility, which is you have small particles, then you become bigger particles. Okay, so for this case, right? So first of all, this is gamma what? Tell me. This is still before and after. This is before sintering and after sintering. So obviously this one, it is still gamma. Let me see the answer. Yeah, still gamma SV, SV, but the surface area changed. Okay, surface area of 1 is this. Okay, so for example, before we have n number of the small particles, but now the same volume, we are going to have n prime number of the spheres because sphere become bigger, so obviously number will become smaller. So again, we have this conservation, the volume conservation or mass conservation. So the n times okay, if this is R1, for example, smaller one is R1, and this is R2. Okay, so then it's going to equals to, because this is volume, right? M prime times 4/3 pi R2. Okay, so you can see, right? Because the volume, this is volume of each particles times number equals to before and after. Okay, so using this one, very quickly we can get the n. Obviously, n will be much more, right? Or much less, right, compared with m, because your particle become bigger, so you have less numbers. So in this case, you will see, so m prime is going to equals to 1.875, and now the is 10 power 10, but this one originally you have 10 power 14. Okay. So have you, any of you have already calculated this one? What's the final answer? What is the surface energy of this one? Can someone type? I'm just checking whether you have done any work before you come to this tutorial. Thank you. Okay, Jay and Li Qixia both said 6. Excellent, excellent. I'll give you 1 extra mark. I'm just joking. Okay, let's continue. Okay, so total area will be m prime, a number 4 pi, because now this one becomes bigger, so will be 5 times power minus 6. Okay, because we said this is a micron, we change to meter. So you have 2 times this 10 power minus 6. Okay, use this is area of 1 particles times number, you will get 5.9. Okay, we times gamma, which is gamma SV 1, so it's roughly 5.9. Give me 6 also can. The 1 point still valid. Okay, so now we very quickly move to our final conclusion already. So you can see, so now I'm asking you, so is this one going to happen? Yes or no? Can you type? So do you think this one, when you heat up, so the particle change from smaller to bigger? So do you think this is going to happen? Yes or no? Okay, I only see 1 yes. Can someone type more? Thank you. Yeah, Usman. Okay, so thank you. Very good. Very good. Okay, so yes, it is going to happen, right? We said, because again, you can either become this bigger one, because this is only 6. You start from the 118, okay, and also this one is 92. You are going to, both are going to happen. That's why we said these two are competing. Okay, so which one is root? This is root, cosine is root what? Tell me. Cosine is root. So we said there's 2 root competing, right, in sintering. So this is root. Cosine is root, let me see. Jay, thank you. Thank you. So yeah, 2 cosine, okay, root 2 and root 1. So both is going to happen, and they are also competing with each other. Okay, so the driving force of sintering is reduce the total surface energy. Okay, so that's what we said here. So there will be 2 ways in competing. So what we calculate this one in class, which is densification case, and just now we calculate the second case, which is coarsening. Okay, we have calculated both. So we are seeing that both of them are going to happen. But the thing is, and they're competing. Oh, we hate competing things, which means we have to make choice. Okay, so obviously, if you want densified structures, you will definitely have to go to root 1 or 2. Can quickly type. Udena? Excellent, excellent. You need 1, right? Excellent. Okay, so this one give you densified structures, and this one give you porous structures. So for example, we have already seen here, right? This one is a root 1, right? Densified. So you can see, so when you become bigger and bigger, so the density is nearly reached to 100, which means that very densified already. Okay, so right density. Okay, but this one, the grain size, is become very big, but at the same time, the density does not really change much. Okay, so this is pure coordinate, so this is 2. Okay, so extreme case, 1, 2. But the reality, life is real. Okay, so life is always someone here, right here. Okay, so you always is 1 plus 2, root 1 plus 2. Okay, so that motivate us to learn how can we control all the centering to get more root 1 or more root 2. So this is going to what we're going to learn this Friday. Okay, so how can we control in the centering to make root 1 happen more or root 2 happen more? Because in the end, what is centering? Tell me. What is centering? So you have particles, right? You have particles. So the particle come together, right? So there's atoms inside, am I correct? There's atoms inside, okay? So it's all about where will this atom go? Can you imagine? So in the end, it's all about where will this atom go? So the principle is atom will always go to where? Tell me. Atom will always go to the higher or lower energy side. Tell me. Higher or lower? You just need either type higher or lower. Excellent. Very good. Very good. Thanks, Chishan, the J. Okay, excellent. Okay. Okay, so that's justify us to come out this Yang-Subs equation and the Kelvin equation. We said Yang-Subs equation and the Kelvin equation tells you that all this free energy per one atom is actually inversely proportional to R. Okay, that's the special thing of the centering, because centering is what? Centering is you have particles and particles have radius and they come together, right? They come together to form certain things. Okay, so they will have all sorts of atom movement, move from where to where. Okay, so this is question 5. Question 5, we actually, you already say, right? I only change what? I only change what? Can someone type your answer? What's your final answer? One more extra point. Again, joking. Can someone type? You already done at home? Have you done at home? What is the final answer if I change the radius to, are you sure? 17.6? I can't remember. Okay, anyway, 17.6. Let me double check. Okay, I can't remember anyway. So when I change from 90 to 900, what will happen? Okay, so for example, we have to explain this one again, right? So what is this Yang-Subs equation? So Yang-Subs equation, there are different ways to explain Yang-Subs equation. Okay, for example, so this is a more simple way for you to understand. For example, we said if you have a balloon, right? So balloon at any place, you need to have this mechanical equilibrium at any place. Okay, so for example, if I only take the middle, this cross-section, middle cross-section, okay, so you can imagine, so this piece of the materials, middle section is under 2 force. So one force is coming from the pressure difference, right? Because inside have higher or lower pressure, tell me. Inside have higher pressure or lower pressure? Can you type? Inside, outside? Yeah, at this moment, just use common sense to judge first. Okay, inside actually you have higher pressure. Okay, higher pressure inside minus outside is delta P, right? Delta P is P inside minus P outside. Okay, okay, so delta P. Okay, so delta P times what equals to force? Tell me. Delta P times what equals to force? Excellent, area, excellent. Okay, good, thanks, Ho-Chin. Okay, thanks all of you. Okay, so let's continue. Okay, so we said delta P times area equals to force. Delta P is, so area is pi r squared, because this is okay, radius of this sphere of the balloon. Okay, so then, as I said in the class, right, so this pressure difference is going to be balanced by which one? If it's in balloon case, balanced by what? Tell me. Its balloon case is actually balanced with the stretch of the rubber, right? Am I correct, right? Because rubber is the one containing everything. Okay, so again, if stretch of the rubber, so you can imagine if now we have a force here, which is gamma SB. So we also need to know, so this stretch of the rubber happens at where? Again, give me the keywords. Give me the keywords, please. The rubber stretch at where? Gamma stretch. Okay, so the gamma SV need times length, right? Length equals to the force. Okay, what is this length here? Tell me, what is this length here? So it's the rubber, right? Rubber. Yeah, circumference. Very good. Circumference. The circumference. Because rubbers happen at this whole area. The circumference. This whole circumference is the length of the whole rubber stretching. Correct, right? Okay, so that's what we put here, 2 pi r. 2 pi r is the circumference of this rubber. Okay, and we say times gamma. And also these two have to be in balance. So very quickly, you will see delta P equals to 2 gamma over r. Okay, so this is actually my way of more like analogy for you to remember these whole things. Okay, but actually in textbook, people always use the second way, another form of Young subsequation. Okay, so this is more written and rigid in the class textbook. So we call it delta mu. So what does this delta mu mean? Okay, so for example, I have atoms here, right? So this is a whole particle. So this particle have a radius which is r. Correct, right? Radius which is r. Okay, so now I'm going to ask you, because the particles you have full of atoms inside. Full of atoms inside. Okay, so you need to calculate the free energy per 1 atoms. Correct, right? Per 1 atoms, because in the end, he need judge where I'm going to go, because I'm going to go somewhere which give me my lower energy. Correct, right? So how can we do? So again, we use the same old tricks of material scientists. Okay, we always use the same way. Okay, so first of all, we calculate total. So total, this is gamma SV. Okay, so you times what? You times whole area. So which will be 4 pi r gamma surface tension per unit. Okay, so then also you need, because this is a whole as a particle, but I need divided by what? Equals to the per 1 atoms. So very straightforwardly, what you need divide by, so you need divide by how many numbers of atoms of this atom, right? So let's calculate how many of this inside you have. 1, 2, 3, 4, 5. So let's calculate. Again, as material scientists, we have a simple way to approximate. So we just simply need to get the total volume first. Total volume first. Okay, 4 pi r cubed over 3. So that is the total volume of these particles. I divided by the volume of 1 atoms. So this one we call it atomic volume. Okay, why the arrow is a bit shifted? Okay, so this one is atomic volume. Okay, atomic volume. Okay, so atomic volume. Okay, so you have the total. You have the total here. You have the number here. Okay, so the rest is just a simple mass manipulation. You do the differentiation. You give you this one, which will be the 2 gamma over r again, because this is constant. It's again the only change things is the r here. So that's why the particle size is so important, because the particle size determines the free energy per 1 atoms. Okay, so now I'm asking you, now start to answer questions. Okay, a particle A and the particle B. So can you type? So the particle will move from A to B or B to A. Can you type? A to B or B to A? A to B or B to A? So first of all, I see different answers now. So first of all, which one have higher free energy? Is A, the atoms inside A have higher free energy, or inside B have higher free energy? Which one have higher, A or B? Now everyone get the same answer. Yes, so B have higher energy. Am I right? So B's have a high energy. So obviously B will go right? Because A have low energy, which means B will go to the A. So in the end, it will form a bigger one. Okay, so that is the first question. So the small one will move to the bigger one. Okay, the small shrimp will move to the big fish to get it up. Okay, so this is the first question. My second question now, I have a particle A, and the particle is not particle like outside, but it's like a flat one. Okay, particle A and particle B. Okay, now, so the particle is going to move, the atoms inside is going to move from A to B or B to A. A to B or B to A. A to B or B to A. So again, if it's a flat surface, so now tell me what is the R now? If it's a flat surface, R is equals to what? R equals to what? No, flat surface is equal to 0. No. Like yeah. Okay, yeah, okay. If it's a flat surface, actually the R is equals to infinity, right? It's just like our Earth, because our Earth has such a huge radius. That's why we feel it's a flat one. Okay. Okay, so now, can you answer now? So the atom is going to move from A to B or B to A? A to B or B to A? Odella said A to B, agree? Qixang said A to B, correct. Do you agree? Yes, thank you, Ho Qing, Odella, and also Qixang, correct. Okay, so we said it's going to be from A to B. Why is so? Because once if it's flat, which means the radius is the largest possible, so infinity. So it's always moved from smaller r to bigger r. Okay, so that's what we put here. So in this case, this one we call it a convex. Convex more or less like a balloon. So which is the one we are very familiar. Any spheres, they have a radius which is positive. Okay, so the convex R is larger than 0, so delta mu is larger than 0. So the chemical potential of the atom on such surface is actually larger than that on the flat surface. Why so? Because the flat surface, the R is actually equals to infinity, the largest possible. Okay. So again, we also talk about this Kelvin equation. Kelvin equation give you one more factors, which is temperature, but not really used that much. You can say all these are constant, everything's constant, except R again. Okay, so as I said, I'm not requiring you all these things, but just use this equation. You can have all sorts of forms, variations. So P equals to P naught exponential 2 gamma with this molar volume RT. Okay, gas constant. So all this can simply just use equations. So now we are very safe to talk about our questions, right? Okay, so we already done this in the class. The molar, this molar volume, which is mass divided by the density. Okay, so we can get the molar volume. Okay, which is this. So we put all this value in. So you can see. So 2 gamma. This one is constant. You can say all this is gas constant R. This temperature please change to this Kelvin. Okay, and this is gamma. And also you can have all sorts of number, doesn't matter. So this is just you can get from the website. Okay, doesn't matter. Okay, so then we continue to, and this is molar volume. Okay, so this is radius. Okay, radius because 90. Okay, so from here we will know that it's 17.745. It just now Qixang you said how much, I can't remember. 70 point something. 6. Okay, let me double check. I don't know whether correct or not. Okay, so how can we do? So what we put is okay, same thing. So we just follow the same question. We put 0 here, right? We put 1 0 here. So which means we have 1 0 here, right? So which means we're going to have 1 0 here. Yes, are you correct? Okay, 17.745. 17.745. Oh, sorry. It's 17.555. Sorry. That's why I saw it's a bit strange because Yes, 6, 70.6, also can, also can. Okay, so doesn't matter. Okay, so anyway, so all these things, the examination calculation is not required for this question. Okay, no worry. So you just need to keep to constant. Okay, okay. So Tor, I know there's a bit the tricky things to convert because if you have websites, very easy for you to check. Okay, but I don't really require this in the real examination. But why we have this question? So now my next question is, tell me. So the atom will move from 90 to 900 or 900 to 90. Atom move from where to where? 90 to 900 or 900 to 90. J, 900 to 90. Atom move from where to where? So this one is 90. This one is 900. So we move from where to where? Atom will always move from higher pressure to low pressure, or low pressure to high pressure. Yeah, thank you. Thank you. Thank you. Yes, yes, yeah, yeah, typo. Okay, thank you, Jay. Thank you, Jay. Thank you. Okay. Okay, so yes, from 90 to 900. That's our question now. Okay, so which is this case? Okay, so either move from small to big or big to small. It is from the small to big. Okay, because this one have higher either free energy or pressure. It doesn't matter whichever one you use. So this one we call it Osborne rippling. Okay. So that is this question. Okay, so we can quickly recap already. Okay, we only have 5 more minutes. Okay, and we learned that specific coordination number, there will be a critical or minimal. These are the keywords. If I use a different color, critical or minimal RCOVA, so for which the contact can be maintained, and follow the steps. So we have 6 steps, but actually the most important step is step 4, right? Which is the width ratio. Make sure you calculate the right width ratio. Okay, and also coarsening and densification will reduce both of its energy. Okay, so we calculate this one in the class, and just now we calculate this one in the tutorials. We know that they're going to competing. So how, as a material scientist, we can make our atoms move from more to coarse densification or more to coarsening. We have the tricks, and the tricks is coming from where? The tricks is coming from this Young substitution and the Kelvin equation. Okay, it's simply because the free energy per 1 atoms is different. It is inversely proportional to R. Inversely proportional to R. Okay, so just now we already said this R is obviously R is larger than 0. Okay, right? It's the balloon case. The balloon case is the one you're more familiar with. Okay, so in this case we call it a convex. Okay, so convex, okay, have the R larger than 0, so delta mu is going to be larger than 0. But if it's a flat one, so R is infinity, so delta mu is equals to 0. So it's just this, if there's no shape constraint, so it's just outside, right? Just same, okay, we just said like a balloon. So balloon inside, we have a pressure, right? Outside, you also have a pressure. So actually, this outside is actually supposed to be the R equals to the infinity case. Okay, so R, which this Pinot is supposed to be the R equals to infinity case. Okay, so that's why we said delta mu is actually in this case equals to 0. Okay, so then we said, so the atom is actually moved from the small to big. Okay, and also in this case is from radius to something infinity. Okay, so so atom, the free energy of atom highest at the convex, followed by the flat, and followed by the concave. So at this moment, I know the concave case is a bit confusing. So no worry. So we are going to know more in this Friday's class. Okay, so actually in this case, in mathematics, we define if it's a concave, so this R actually is less than 0. So in this case, delta mu is actually less than 0. Less than 0, which means the pressure or delta mu here is, the mu here is actually less than this R, because this R is a Pinot, right? But it doesn't matter. I know at this moment, it's a bit confusing here. We ignore this one first, okay? But we have already know that the atom is going to move from the convex to the flat, because the flat one gives you the R, which is the infinity. Okay, so that is all for today. So see you this Friday.